All right. So, perms and coms. Permutations, order matters, combination order doesn't matter. We're going to talk mainly about permutations at first, then we'll get to combinations. But I just kind of want you, we're going to come back to this list at the very end to reaffirm what we know, but right now we're just kind of going over the differences. So permutations, order matters. So you have to think about whatever you're doing. If you change the order, will it change what you're doing? So for example, a PIN to get money out of the bank. If you say order doesn't matter, then your PIN of 4321 could be put in as 1234 and you'd get your money out. Is that real though? No. So PINs are permutations because the order matters. Words. So if you said order didn't matter, then meet and team would be the same word. And is that true? No. So order matters. So if you take whatever it is and you move it around and you get something new, then order matters. So words are permutations, pins are permutations, license plates are permutations, because if your license plate is BBF, no one's going to take BFB as the same license plate, right? Because order matters. Another thing that order matters is if you choose people for a subcommittee and give them jobs. Because then the order you pick them gives them a different job, right? But if you said you picked a 3-person subcommittee and that was it, would the 3 people and the way you picked them change if they were just going to be on the subcommittee or not? No. So then it would be a combination. So here's an example. If in this class I let you, I was going to give out 3 prizes, okay? Just randomly choosing names. I was going to give out 3 prizes. What if the prizes were all the same? Would the order matter in which you were picked in those to get those 3 prizes? No. So that would be a combination. So if your prizes are identical, or the jobs for the subcommittee are identical, then it would be a combination because the order wouldn't matter. Now, how could I change it to a permutation? That exact same example where I gave you 3 identical prizes, picked your names, it was a combination. How could I change it? Yeah. Yep. So you can do jobs at different levels of difficulty. So that would change your subcommittee to a permutation. What about if it was prizes? What could you change in order to make it so that it did matter what order you were picked? Anyone have any idea? Instead of identical prizes, what would you have to do? Yeah, just different prizes. Because if they're different, then the order matters, right? Because then if you wanted the Skittles, which was the second prize, you would hope to get picked second, right? So if they're different prizes, the order matters, the permutation. Combination locks annoy the heck out of me. Because what should a combination lock be called? A permutation lock. Because does the order in which you put the numbers into your combination lock matter? Yeah. If the code is 29328 and you put in 28329, you're not getting in, right? So combination lock should be called permutation locks. If people are standing in a lineup for a picture, some people say, well, order doesn't matter. Order matters if when you look at it, it is different, correct? So if you're lining people up for a picture and I stand in the middle and in the next picture I stand on the end, can we tell the difference? Can you see a difference in that picture? Yeah, so then order matters. So the moment you arrange anything or order it, it's called a permutation. So that's why I'm going to put down here a little star. If it says arrange or order in the question, it's a permutation. Arrange is mainly the one. Order would give it away, right? So they often give arrange. How can I arrange these people in a line? Or how do I arrange these books on a shelf? If you're arranging them, you're making the order matter. Now, how could you make order not matter? Well, arrange 3 exactly the same textbooks on a shelf. Would the order matter then? If I rearrange the 3 exactly the same, exact same textbooks? No. But if I had 3 separate textbooks, one was a grade 12, and one was a grade 11, and one was grade 10, could you see the difference if I moved them around? Yeah, then it would be a permutation. Winning first, second, and third, that is an order matters because first is better than second is better than third. And then itineraries. Itineraries mean you have to go here first, then here second, then here third, so you're giving it an order. And then combination examples are handshakes. Handshakes a combination because there's not like there's a middle line that when someone reaches it first, you got there first, and therefore the order matters. Two hands come together, they shake, boom, you have a handshake, right? So there's the order in which hand reaches the other one first, and I don't know what's first. Like, do you draw a line in the air and then gets it? Like, so handshakes order doesn't matter. Card hand order doesn't matter. There's the odd card game, which I've never seen ever on a test, that does matter, like war. Order would matter because you just have to play them in the order that they are in the pile. But most of the time in most card games, the moment you're dealt cards, you put them in your hand, and what do? You move them around. And if you move them around, does the order matter? No. So the moment you get 5 cards in your hand, say you wanted, I don't know, you needed 2 queens and 3 kings, let's say, right? And they're out of order in your hand. Do you still have 2 queens and 3 kings? Yeah. Could you be the person like me who organizes pursuit or organizes by number downwards, depending on what the game is, or a vicious like banshee like my child who just puts them all in her hand and like you don't even rearrange them? They're just all different. Like you have different suits, different cut. Like you don't even know what you have. You don't put pairs together. Like who are you? You should just toss them in her hand and goes. Like organize those things. So you don't have to because order doesn't matter, right? It's a card hand. And then there's other options which we'll discuss more. So we're going to go down here to the fundamental counting principle. The fundamental counting principle is you consider a task made up of several stages. If the number of choices for stage A, first stage is A, this number of second choice, second stage is B, choice for the third stage is C, etc., then the number of ways you can do that task is by A times B times C. Well, let's see what the heck that even means. So we have a toy manufacturer makes a wooden toy in 3 parts. Now this is the key thing. You have to need one option from every part, okay, in order to use the fundamental counting principle. So this toy has 3 parts. If all I could do was choose part 1 and then I'd have a toy, you can't use fundamental counting. Like there's just, you need to have, or if they wanted, you could have 2 middle parts, let's say, then you can't use fundamental counting principle. So the key thing here is you need to have each part and you need to pick at maximum and at minimum, so only one option, okay? So you need to have one option of choice from each of these pieces, okay? So say we're making a sandwich. It makes it a little more understandable if you're making a sandwich. You have 3 choices of bread, 4 choices of meat, 2 choices of cheese, let's say. As long as I want one piece of bread, one type of bread, one type of meat, one type of cheese, I can use the fundamental counting principle. But if I want one type of bread, one type of cheese, and 2 types of meat, I can't use the fundamental counting principle. So from each option, you can only pick one. Okay? And it'll make more sense when we show the actual fundamental counting principle. But I want you to understand the fundamental counting principle actually works by showing you it in a tree diagram first. So we're making a wooden toy. Part 1, the top part may be colored red, white, blue, or pink. So there's 4 options for the top part. Middle part, orange, purple, or black. And the third part, yellow or green. And we're making a tree diagram from this. Okay? It's more of like a shrub or a sideways tree, or like a tree that forms itself horizontally against gravity, okay? We don't ever want vertical trees, and you're often not asked to make a tree diagram. The reason why I show the tree diagram is so that you actually trust that when I multiply these numbers together and get an answer, it's real. It actually is the correct answer, not just you trust me and just do what I say, okay? So we're going to list part 1, and then we're going to make sure that we leave spaces between the colors, because each of these colors is going to have some horizontal branches off of it. So if you stack them tight together, you're going to have no room to put branches off of it. So just do what I do. So we start off with red, and then we're going to leave a bit of a space, and we're going to write white, leave a bit of a space, and we're going to go blue, and then leave a little bit of a space, and we're going to put pink, because each of these is going to have branches. So if this toy only had part 1 part, I would be able to make 4 different toys, right? A fully red toy, a fully white toy, a fully blue toy, or a fully pink toy. I would have 4 toys. But this one doesn't have that. It has those 4 options, and then part 2 actually has 3 options, orange, purple, or black. I'm going to be lazy and write O, P, and B. So I could have a red top with an orange, purple, or black middle. Or I could have a white top with an orange, purple, or black middle. Or a blue top with an orange, purple, or black middle. Or a pink top with an orange, purple, or black middle. So if this toy was only allowed to have 2 parts, how many different toys could I have? How many different toys does that give you? 12. And what did we do? We would have just done 4 times 3. Right? But it didn't have 2 parts. It has 3 parts. So we still have to do part 3. So off of every single one of these letters, we have to have yellow and green. So we could have a red top, orange middle, and then a yellow or green bottom. So we're technically just doubling all of the toys we had last time, right? Taking all those 12 toys and we're giving them options of the base. So how many different toys did we get here? Now, 24. We had 12, and technically each of those spots is going to double it. So we have 24 different toys. Now this isn't too bad when there's 24, but like you have, say you have 144 different toys, that would get a little old, and we'd need a large piece of paper for every single question, right? So how does the fundamental counting principle work? Well, I said to you that if you have different parts and you need to use each part, so I need part 1, I need part 2, and I need part 3, correct, to make this whole toy. If I need that, I can put a blank for every part. So this blank is for part 1. This blank is for part 2. And this blank is for part 3. Now these blanks here, this blank here, this blank here, this blank here, those all represent me taking one of those items. Okay? So in each blank, I actually have X number of options, let's say, but I'm picking one of them. And then in this blank, I have X number of options, but I'm picking one of them. And then in this blank, the third blank, I have X number of options, but I'm picking one of them. Correct? So if I wanted to pick 2 pieces of meat, I can't do this because each of those blanks represents taking one option. Do you see that? So if I wanted 2 pieces of meat, I wouldn't be able to do the fundamental counting principle. You'd have to use combinations, which we do way later, which makes sense. So for now, I can only ask you questions where you're literally picking one out of each option, because you wouldn't be able to do them otherwise. So part 1, I'm picking one option, but above I list how many options I have. So how many did I have? 4. Then part 2, I'm picking one of the options. So the blank means, but how many options did I have? 3. And then part 3, I'm picking one option, but I had 2. Now this is the key thing to understand the fundamental counting principle, or anything in this unit. If we use the word and ever, if we say we need this, we will always multiply. So if we can use the word and, we multiply. If we use the word or, we add. Now how I remember this is and add look very similar. They actually look like they should go together. They're one letter difference. They're like, you think they should go together. But they don't. They're so similar they hate each other. They do not want to be anywhere near each other. So and add seem like they should be besties, but they're two actually similar and they don't like each other. Okay? So and does not go with add. And goes with multiply, or goes with add. And add cannot go together. Okay? All right. So I have to ask myself, now the fundamental counting principle says you multiply them. You know the answer is 24, so you know to multiply them. But why? So I have to say, do I need part 1 and part 2 and part 3 to make the whole toy? Or could I have part 1 or part 2 or part 3 and make the toy? Yeah. Yeah, so you have to and them, right? I would have to do this one and this one and this one to make the whole toy, because I need all three parts to make up the one entity. So I'm going to have to multiply. I don't need part 1 or part 2 or part 3. That would mean that I could have part 1 and I'd have a toy, or I could have part 2, or I could have part 3 and I'd have a toy, which is not true. I need part 1 and part 3 and part 2. Now, you can just put dots, which is what I do. If you don't put the dots, which people will forget to put the dots, they'll put the numbers down and they forget to put the dots, you actually have the number 432. You don't have 4 times 3 times 2. People are like, but you know better. No, I don't. I see a 432, right? And people marking are not me either. They're not people who love you. They're just people who don't know you. You are a paper to them. Because even if I figured out that I was marking your test, I'd have to hand it off. I'm not allowed to mark your test. Okay? So you have to go and put the dots, because the dots means you multiply and you're explaining that it's actually 4 times 3 times 2, not the number 432. And you might be like, of course, that's obvious. It's just an accidental thing. Like you just do the question and you know it's 24, you just forget the dots. It's not that you don't know they should be there, it's just an oops, right? So just watch yourself. So then there are 24 different toys. That is it.